Welcome back. We're continuing a manufacturing application of linear programming, and we were given some information and we derived an optimization equation and a set of constraints. So now what we're going to do is, we're going to clear some space here, and we're going to graph these constraints and see where the feasibility region is. All right, so let's go ahead and graph these constraints here. So here is our optimization equation and our constraints down here. So let's go ahead and graph this. So here's our y-axis. This is our x-axis. This is the positive y direction. Here's our positive x direction. And let's go ahead and draw our graph. We're using linear programming, and we want to maximize the total profits of this company, of this manufacturing company, given a certain set of constraints and the certain profit of widgets. So we have this optimization equation down here. Let's go ahead and scale this by hundreds. We can just look at our values down here, and we can get a pretty accurate scale. It doesn't have to be perfect. As you saw in the previous application, we were actually a little bit off on our scale. But if you recall, we're just dealing with when we're graphing a system of linear inequalities, we're actually just, or actually anything, just equations or linear inequalities, we're just trying to get a feel for the actual visual representation, and not we're not trying to be incredibly accurate. It doesn't have to be perfect. So let's just go ahead and scale this a little bit. We're scaling by hundreds. The x-axis represents the total number of widgets A produced. The y-axis is the total number of widgets B produced. And we came up with an expression relating x and y to find the number of widgets C produced. So here's our optimization equation, and we want to find the values for x and y that give us maximum profits. All right, so let's go ahead and graph this. So let's take a look at our first constraint. Our first constraint is, let me get a different color here, is this one right here. So we have y is less than or equal to 1/3 x. So let's go ahead and graph this. So when x equals 0, y is equal to 0. So our first point on this line is going to be right here at 0, 0. Our second point we can find by using the slope. It has a positive slope of 1/3, which is going to be right here. So we connect these two dots with a straight line. And, well, maybe we made it a little too long. And this is going to continue infinitely in the positive direction. Now notice this is a solid line. Actually, all these constraints are going to be solid lines because they're all either less than or equal to or greater than or equal to. All right, so we want to pay close attention to that. So let's look at the next one. Next, we have, let's go ahead and do x is greater than or equal to 0. What this is going to do is it's going to give us a vertical line about the y-axis. This is going to be right here. This constraint and the next constraint are actually going to be very intuitive. So this is going to be x is greater than or equal to 0. Let's go ahead and label these. This one is going to be y, it's defined by the inequality y is less than or equal to 1/3 x. All right, let's go ahead and draw our next constraint. Our next constraint is going to be y is greater than or equal to 0. Y is greater than or equal to 0 is going to give us a horizontal line that's superimposed on the x-axis. It's going to be right there. It's going to continue infinitely in this direction, and this makes sense because these two constraints, which are extremely important, they tell us that all of our values are going to be in quadrant 1. And this makes sense because we can't produce a negative amount of widgets A or a negative amount of widgets B. We either produce a positive number or we produce none. So I've used a little intuition. This actually makes perfect sense. This is the inequality, the constraint, y is greater than or equal to 0. Let's graph the other ones. So we have next, we have, let's go ahead and do this one. We have y is greater than or equal to 800 minus x. So when x equals 0, y equals 800. So it's going to be the point right here. And we have a slope of -1, so we're going to go down 1 and to the right 1. So this line is going to be straight like this, and it's actually going to pass right here to 800. So we're going to imagine that this line travels through this point right here. If we squint really hard, we can see it. And it's going to be described by the constraint y is greater than or equal to 800 minus x. All right, let's go ahead and take a look at the last one. The last constraint we have is y is greater than or equal to 1000 minus x. When x equals 0, y equals 1000, so it's going to be right here. And it also has a slope of -1, which is going to be parallel with the blue line. So these two lines will never intersect, and it's going to not cross the x-axis. It actually can, but we're not interested in any values below the x-axis, because remember, we can't produce a negative amount of widgets. Okay, so we have our constraints graphed, so let's go ahead and find the feasibility region. The feasibility region is the set of all points that satisfy this system of constraints. So, and what we do is we just go by process of elimination. Well, we've already eliminated 3 whole quadrants because of these 2 constraints. We're only dealing with quadrant 1, to the right of the orange line and above the green line. And this makes sense because we're looking for positive x values and positive y values. So let's go ahead and look at this one, this purple line. We want all the values that are underneath this purple line because we have a less than or equal to sign. So we've narrowed it down to this section right here. Our next one is going to be, says our values are going to be greater than the blue line, so to the right and above the blue line. So we're looking for this section. And our next one is less than or equal to y, or this red line, which is over here. So our feasibility region is going to be this section right here, including all the points on the 4 lines on the perimeter. So this is our feasibility region. We label this our feasibility region. Feasibility region. For some reason, I seem to spell that one wrong quite often, so let's go ahead and write this one out. And we need to label this one. This line was the constraint y is less than or equal to 1000 minus x. Okay, so we have our constraints mapped. We have the feasibility region confirmed. Now, what we want to do is, instead of trying to plug in every single point included in this feasibility region, which is theoretically impossible, we only want to look at 4 points. We know that one of these 4 intersections, or the corners of the feasibility region, is going to give us a maximum and going to give us a minimum value for our optimization equation. These are called extreme values. We're not worried about the minimum value because if this is our profit equation, we want to maximize it. We want to maximize our company's profits. So what we're going to do is we're going to use these 4 intersecting points, given these 5 constraints, and we're going to set the appropriate equations equal to each other, also called a system of equations, so we can solve for a given value. So we can get an x and y value for each one of these points. Now this makes sense because when these given constraints are equal to each other, that means that that's where they intersect. So we'll actually do that in the next video, and then we'll get our x and y values and plug them in one at a time to our optimization equation, and whichever gives the biggest value, that's actually what's going to maximize our optimization equation. So I'll see you in the next video.